Hi, I'm Keller VandeBogert. I'm a student at the University of South Carolina, and my advisor is Andy Custon. Um, yeah, let's get started. So I just briefly want to go over my interests. So I'm interested in the construction of free resolutions, computation of homological invariants using these resolutions, and moreover, just general DG techniques. In particular, I do really like to use these kinds of techniques for things that arise in the context of some other branch of mathematics. So let's get into what I've actually done. So for research, we have all of these little dots to click on. So the first one I want to look at is trimming complexes. So trimming complexes were something that were a generalization of a complex that had appeared in my earlier work working with type 2 compressed strings. And the idea is to think about taking a generator of an ideal and then replacing that generator with a rescaled version. So you rescale a certain generator by an ideal. So a quick example is written below. So you have x squared, y squared, z squared. And then what I'm going to do is I'm going to rescale z squared by the ideal x, y, and z. And so what a trimming complexes do, well, a trimming complex is going to find a resolution of this new trimmed ideal in terms of the resolution of the ideals x squared, y squared, z squared, and the ideal x, y, and z. So let's move on. So the next thing we have is compressed rings. So for compressed rings, in my case, I've mainly focused on the case for Artinian K-algebras of projective dimension 3. I have a structure theorem for when the Sokal degrees are s and 2s minus 1 for any s greater than 2. And kind of the main punchline that comes out of this work is the surprising fact that this can be used to reduce rings of arbitrarily large type with Tor algebra class G. Previously, it was a conjecture of Avramov saying that if you are class G, then you must be Gorenstein. Christensen, Velike, and Veyman had constructed type 2 counterexamples. The counterexamples that I was able to construct encompass their counterexamples, and I also provided arbitrarily large type counterexamples. So let's move on again. So next we have DG algebras. So one of the things I've done is I've taken the length 4 big from small construction. This is built by Custon and Miller, and I've endowed this with the structure of an associative DG algebra. This was already known before in the case where 2 is a unit in the ring that you care about. But I generalized it to arbitrary characteristic. I also use different techniques. So this method of proof is entirely self-contained and different from the original way. Another thing I've done, so I compared the DG structures of the Eliaou-Cravair complex and the L complexes of Buchsbaum and Eisenbud. It was a question of Pava as to whether these two DG structures coincided. So what I did specifically was I found an exact isomorphism of complexes and showed that using this isomorphism of complexes, the induced DG structure, it does not coincide with the pre-existing DG structure on these complexes. In this same paper, I also find a class of ideals whose minimal resolution is a DG subalgebra of the Eliaou-Cravair resolution. All right, so next I want to talk about my work with monomial ideals. I've mainly focused on equigenerated monomial ideals, that is, ideals generated in the same degree. And kind of the new perspective I've brought is to study the equigenerated monomial ideal via its complementary ideal. And the idea here is, instead of looking at the generators that this ideal does have, take the opposite perspective and look at the generators that it does not have. And based off of the properties of the generators it does not have, or the generators you've deleted, deduce what has to be true about these ideals. And so under certain conditions on the complementary ideal, I can compute explicit Betti tables and construct explicit linear strands for these ideals. All right, last, let's move on to determinantal facet ideals. So this is all joint work with Aya Al-Musa. And in this case, the main case that we care about is to focus on the case that the minimal generating set forms a reduced Grosvenor basis with respect to the standard diagonal term order. Kind of the big results coming out of this are, we prove a generalized version of a conjecture of Eine, Herzog, and Hebe, which states that the Betti numbers of the original ideal and the initial ideal coincide. We prove this in all possible cases except for the binomial edge ideal case. That is still open. However, almost as good as we at least construct an explicit linear strand for the initial ideal in all cases, including the binomial edge ideal case. One consequence of this is the fact that the linear strand Betti numbers of the initial ideal and the original ideal agree no matter what, so including the binomial edge ideal case. And I think that's all I have. So if you're interested, the research tab on my website is a good place to find all the papers that I just mentioned here and more. So thank you.